There is a little-known truth buried under the concrete of Cold War bunkers, missile silos, command centres and listening stations. It wasn't the steel, the blast doors or the reinforced concrete that ensured these structures stayed operational for decades under immense pressure. It was something far more subtle, an invisible defence layer that kept moisture out, protected electronics, and stopped corrosion from eating these facilities alive. During the Cold War, engineers quietly developed one of the most advanced moisture control systems ever deployed, and without it, many of these underground structures wouldn't have survived a single decade. Today, we're going to dig into that overlooked technology, why it was crucial, and how the very same principles can be used in modern shelters, homesteads, and off-grid construction. Stay with me, because by the end of this, you'll understand why Cold War engineers treated moisture as seriously as radiation, sabotage, and blast pressure. The story begins with the Cold War's obsession with underground survival. Once nations started carving command centres into mountains and burying nuclear infrastructure beneath layers of soil, a new problem emerged. Underground spaces sweat. Moisture seeps through concrete, condenses on walls, corrodes metal, shorts electrical systems, and undermines structural integrity. Early on, engineers realized that a nuclear-resistant bunker was worthless if the wiring inside corroded, the communications arrays failed, or mold compromised living quarters long before an attack even arrived. This is where the breakthrough came. Cold War engineers designed multi-layer moisture barriers capable of stopping vapour, capillary movement, and even chemical intrusion. Their methods became a guarded engineering toolkit because these weren't ordinary building materials. They were strategic assets, ensuring that underground bases could remain functional for decades without intensive maintenance. Understanding why vapour control became a life-or-death requirement for underground facilities is, well, pretty eye-opening. In a sealed bunker, moisture doesn't just cause discomfort. It destroys mission-critical equipment. Radar components, vacuum tubes, missile wiring harnesses and radio systems all fail rapidly when exposed to humidity. Engineers evaluated every failure path and discovered that water vapour, not liquid water, was the most dangerous enemy. Vapour is microscopic, persistent, and capable of passing through concrete, plaster, and grout. Once inside, it condenses on cold surfaces near electrical systems, forming droplets that cause corrosion or shorts. To counter this, Cold War bunkers used vapour barriers that were far more advanced than civilian building wraps. Early versions included asphalt-soaked craft sheets, but within a few years the technology escalated to multi-layer polymer membranes, lead-laminated sheeting, and heat-sealed barriers that created an almost hermetic envelope around sensitive interiors. For example, the United States NORAD-Cheyenne mountain complex used layered vapour defences around electronics chambers, while Soviet missile silos integrated continuous sealed membranes beneath their concrete shells. These weren't optional, they were survival systems. Now, exploring why lead-lined membranes became the gold standard in high-risk rooms is actually pretty fascinating. Lead had a unique advantage that went beyond shielding. It is impermeable to vapour, unaffected by long-term dampness, and capable of being bonded to rubberized or polymer backings. Cold War engineers found that a thin sheet of lead sandwiched between flexible membranes could do two things at once. It blocked moisture completely, and it provided secondary radiation damping for sensitive sensors. In early radar analysis rooms, where even micro-corrosion could wreck precision electronics, these lead membranes were heat-welded into continuous sacks that lined the walls, floors and ceilings behind the finishing layers. When you stepped into one of these chambers, you were essentially entering a sealed capsule hidden behind concrete. In some Soviet installations, the membrane extended under raised flooring to protect communication cables. You can apply the same principle today when building an off-grid bunker or root cellar by installing a continuous impermeable barrier behind the wall, with seams overlapped and heat-sealed or taped. While modern builders would use polyethylene or EPDM instead of lead, the functional logic is identical. Create a continuous vapor shield that cannot be punctured by capillary moisture. When we look at how capillary breaks became the silent guardian beneath every Cold War foundation, it's quite fascinating. You see, water doesn't always move as a liquid. Capillary action actually lets it climb inch by inch through soil and into concrete. Cold War engineers realized that even if you built a bunker on high ground, it could still slowly wick groundwater upward. The solution then was to build capillary breaks, layers that interrupt water's ability to climb. In the early designs, crushed stone was the preferred method, because its irregular surfaces create air gaps that are simply too large for capillary movement. Later on, engineers added polymer sheets, drainage mats, and underslab membranes that serve both as vapor barriers and capillary breaks at the same time. Now, if you're building a small storm shelter, a buried shipping container workshop, or even an underground food store, you can apply this principle by placing a coarse gravel layer beneath your slab and integrating a continuous waterproof membrane above it. Even at a homestead scale, this dramatically reduces moisture problems, mold, and corrosion. Let's talk about how these Cold War moisture systems can be adapted for modern survival-minded builders. You really don't need a military budget to borrow these concepts. A modern vapor barrier is simply a thick polyethylene membrane, continuous and sealed. A capillary break is just gravel under a slab or a drainage mat against a wall. A sealed interior membrane can be assembled using EPDM or reinforced roofing rubber adhered behind panelling. The practical steps are, honestly, quite straightforward. First, you stop vapor at the outer boundary using a continuous membrane. Second, you create a capillary break beneath the structure. Third, you seal the interior around sensitive equipment, tools, food storage, or electronics. These three layers echo exactly what engineers used in nuclear infrastructure, and they remain proven, durable, and accessible today. If you enjoyed this deep dive into Cold War engineering, make sure you subscribe, share this episode, and join the community that keeps forgotten technologies alive. The more we explore, the more we uncover. Relic logic